Hey guys, so today we'll just start with what are the components that I have for this manipulator. And before that, I have a kinematic diagram of what the complete setup will look like after building this entire setup. Right now, I am just showing these two links, which are A1, A2, and the gripper. And we consider four servos, and the one you can see that there is one is mounted to the base, and we have all the other four. But the one will be neglected here because that will be used for the gripper and they don't really manipulate the actual robot arm. Only these three servo motors actually sets the tone for the orientation part. Okay, so make sure that if you're building this from scratch like me, ensure that you use the most solid base that you can find and use that, because the I thought like, okay, servers will not be that rigid, but they were really strong, but they do have their limitations. And based on the kinematic diagram, I have just manually, with the connections using my ESP32 cam and the external power supply, I've just made a small testing layout for each servers in such a way that I mark the 0 to 180 degree. Since these sort of servers cannot rotate on a complete one cycle like 0 to 360 degree, it rotates only to 0 to 180, so we have to bound their limits, but it shouldn't affect our kinematic diagram that we have. So in the setup, if you look, the server is mounted to the one inside of this solid base, because that is the complete limit that the robot arm can get to. So you make sure that you do that as well if you're building this from scratch. So if you look here, I have a custom made L-shaped pipe. It's just made out of pure pipe, and I do have a link on how I made that. Not exactly that L shape, but how we can convert a PVC pipe into something like a sheet, and then you can just fold it up in the natural way how you want it to, any way you need. It is a really great hack. You don't need any hot gun for that. I just pasted the link in the description. If you want, you can just go and look at it. So based on the kinematic diagram, the server should be placed to something like it, and mostly I think the link lens will not be exactly holded by that server, but until we fix that naturally and test it out with that ESP32 cam, we cannot exactly be aware of it. But right now, the ESP32 in that microcontroller, we just write abstracted code like using Arduino IDE, I mean Arduino.h files. But later on, we will be getting into the pure coding, and that part will be writing actual codes. Watch in the next. Hey, so this is day 4 and it's not actually day 3 afternoon. The thing, when I was trying to assemble this all into a full complete manipulator, the first thing was the link length issue. The second is the more way the gripper becomes, it is much harder for this second servo or frame 1. If the index is 0, it is hard for the frame 1 or servo 2 to rotate it. That is was a key learning. Though I've tried, I know that we need to reduce the weight as much as possible, because these all three servers is given to the pressure of the frame 0 or servo 1. So we should, as possible you could, if you're making it from scratch like me, make sure that you minimize the weight as much as possible. I got this screw bolts, especially not from the shop. It's just bought, just took from Compass. That's it. So make sure, like, what I've learned is, if that servo could now hold the weight of this entire setup, like the child frames, that means that server could now rotate the entire setup to the other direction. That is what is my learning. So if now this server could weight or hold this entire setup, that means this server could rotate this entire gripper. This servo is not considered because this is just for the gripper to lock its finger. You can call it something like that. So this is the entire setup. And right now, I've just tested this out with all these three wires, just individually with all the three servos. And what I found is that right now what we are doing is completely fine if we are just for testing it, whether the server could actually rotate the entire setup. But this is not ideal if we have to make this to behave truly like a actual manipulator. Like let's say there is no, not this, maybe like an apple or something is kept here, and if you want to get it to here, we need to rotate this z-axis, that is servo 0 or frame 0 servo 1 to the other direction. But we cannot just keep the servo 1 powered, that is we cannot just pass electric pulse to this servo 1 alone. We need the servo 2, 3, 4 all to get the same electric pulse, but they don't have to rotate, but instead they have to stay in the same spot where they are, so that they hold the apple and at the same time they can rotate. So this requires parallel processing, and that cannot, I think it can be done, but I'm not sure. To get it to as professional as possible, we need to get them into the actual C++ coding, and at the same time we need to manage the real addresses of registers and send whenever it is required. So the next stage will be the coding part. Hey guys, so welcome to this day 12 midnight actually. So we have this setup with an external power supply. As I said earlier, all these four servo motors cannot be powered singly by just this ESP32 cam through my laptop. So I just unplugged this GPIO 0 from ground because that's how ESP32 cams mostly work. So once we unplug that and if we press the reset button, we get this position. These everything are like a sequential operation. This is just the gripper getting higher degree so that it can hold that object, and it will just rotate to the left and then it will just drop them up again. But here if you see, I just messed that out because if you look, the gripper is actually not symmetrical at all. So but that's not our core part here. It's just about making this pick and place through this microcontroller, making sure that we do that from the core part of how exactly microcontrollers work. So let's just look into the code, and I'll just in the side I'll just show the exact clip for exact lines which executes that specific moment. So now we are in the coding part, and if you look here, first there is a lot of things are actually going under here. There is this tons and tons of files on the left, but these are just downloaded from official expressive manufacturers who gave us this software development kit. Instead of going with abstracted Arduino codes. That's why we are just going with this, where we have just initialized our own registers. It's like, it's not, we are creating these registers. Instead, we just take this as a reference from the technical book that they have provided us with. It's not like I've just gone through the entire book. It's more like I got these ideas from AI so that we can just uncover all the abstractions that we write in Arduino with just digital write. So here, if you look, there are four variables, and each of these variable has its own functionality. I'll just go with an analogy so that you can just get this quicker. Let's assume there is a home, okay, and there will be a main power switch which gives current to all the other switches inside the home, right? So here this enable register is like the main power switch, so which gives the current to entire house. So this enable register makes sure that all the switches here, the pins, will get the power. This clear and set registers or something like, if the set register is kept 1 at this address, there is 32 bits in an address, okay? So if any one of the specific bit is turned on, for that instance there will be an electric pulse. So based on how much duration this bit is getting turned on, that much amount of electric pulse will be shared through that pin. And this clear register is in such a way that if any specific bit from this register is turned on, then the power supply from that pin will be reduced, so which will be just zero. So here if you just have to get some solid understanding in such a way that if you're assigning a value to that register, it doesn't mean like it will persist there for so long. Until that certain amount of duration, if whatever you give them, until then they will be turned on. So here if you look, we have four pins, I mean the four motors that we have in our robot arm. The same I have just defined here. Since we assume that this is a 32-bit, obviously microcontrollers are 32 bits. So here we have just defined it as unsigned integer 32-bit type for pin base, that is for the base motor which is pointing towards the top from the world environment, right? For that I have just given the
GPIO pin number 4. So I've just given this, and at that pin, for that register, at that bit, we need to assign value 1. So this is what I've just commented that here. So this is a manual GPIO matrix. I'll come to this later. We'll just jump directly into the main function. So from there we can just get there. Here the main app main is the way how we have to define this. Everything is just learned from AI, so that we can just get the learning curve much quicker. Even for this all setup, it just took me an entire week. So here if you look, we have this GPIO reset pin. This is nothing but all, especially when it comes to this ESP32 cam, we have a lot of learning path here. A single GPI open doesn't mean that it can only just do a general GPIO functions. Instead, it can be connected to other peripherals as well. Peripherals in the sense memory, SD cards, camera, other relevant tasks that can be given, like any other external sensors can also be given as an input to the microcontroller. So in that case, we need to make this GPIO to be more flexible, and for that we need to reset all these pins. In here, whatever pins we have declared for all our respective servo motors, where is it? Here, the same we have just kept it as reset pin here. This is more abstracted. I have not yet digged deep into it, but for this manual GPIO matrix and for the V task delay, this is still a method, but still all this has its own functionality. Let's first get into this manual GPIO matrix out. The same as we did for the enable register. If you look here, we are turning on the main switch of the house. Here the pins, we are just turning on all these pins only once. Here it's just inside the main function, we are just turning this all only once. This is the loop that which made the hand robot to rotate itself always. So these values will be more relevant if you just understand how the electric pulses and degrees are combined together. It's nothing, just 544 pulses. I mean, not 544 pulses, it's more like for 544 microseconds, if we keep a servo motor turned on, that means that the servo motor will be at 0 degree. If the same servo motor is kept for 2488 microseconds, then that means the servo motor will be to its 180 degree. This is what the general concept behind the servo motors, and these values are just the electric pulses, like how long the electric pulses should pass through the servo motor through these pins. This is for base, this is for shoulder, this is for elbow, this is for grip. If you look, these two are kept in the same 0 degree. While I just designed those mechanical parts, I just made sure that when the servo motor is at 0 degree, the gripper must be loose. And when it gets tighter, when it gets to 180 degree, here I've just made it as not exactly to 180 degree, because then it might break the mechanical joint. So I've just increased it, but not to the maximum. Here it is with this 1800. So that's why it is holding that object and it is persisting with that, so that it doesn't drop that object. And here if you look, we have this vtask delay and pdms statistics. This vtask delay comes from this library called free rtos slash task.h. From this library we are getting this. I did try for making this from scratch, like how we did for this GPIO matrix out, but it couldn't, because there is a specific part in the microcontroller called watchdog, which is something like, if we let's run this code, if we take the single line coordinate s-curve move, this calls this function coordinate s-curve. It is nothing but like a trajectory code. Instead of just going with sine and cos, for the optimization purpose we have just gone with the bit shifting. And the core logic from here you can learn is, like, if we shift the bit by 10 to the left, then it means that we are multiplying by a number 2 to the power 10. And the same goes if we are shifting it by right, that means that we are dividing it by 2 to the power 10. And these are the cubic equation, that for each and every frame, for per frame, these value will be ranged from the current value of the servo motor. Here I would have initialized all those starting base. We have to assume that when I started the video, you would have seen that all will be at the exact position where the kinematic diagram was defined as. So every servo angles was in 0. So from there, we'll get to this values. So here, the start base will be that 544, and the values for these target base, target shoulders are here. The current base is the start base. Why we are initializing this? In the sense, there is another optimization that we can do here. We can't call the global variable to a smaller like to the nested function, because global variables has different scope than the functional variables. So we are just getting all these global variables into into the function one, so that we can just access them always from here to here, and then from here we will be calling that here. And once all these frames are done, again we have to initialize this current base values into this, so that the global variable will be called only twice in the function. But here in the 64 frames we cannot call it, which will just be an another I cycles for the microcontroller. We have to optimize as much as possible, and that's why we have just did this. And these things are just we have to do it. AI models would not exactly do much, but it's just good. That's why embedded engineers are existing, I think. So here, I was here, right? So this 1500 744 will all be normally distributed in such a way that how it starts, like I've just tell the nature for 0 to 1 or 2, like how the nature will be. The servo motor will start slow at the first, and in between the angles will just vary so much. Angles in the sense here, the duration will vary so much, so the servo motor can rotate so much, and at the end, again it will just condense small. I think I have a Python code telling that, but it is not in this folder. I don't want to waste your time either. So I'll just have this entire code and the Python code as well in the description. You can just open any online compilers, and if you want, you can just get to the nature of how exactly these all works. Instead of 10 and bit shifting operator, I would have used the exact values of what is 2 to the power 10, and that's it. So here, what we are doing for each of these frames, we are calling the execute single frame step, and we are passing the current base and current shoulder, current elbow, current grip. Current base, shoulder, elbow, grip are values which range from 544 to the target base value. That is what is the nature of this cubic equation. So but it will start slow. For the 64 frame, it will be distributed in such a way as that cubic nature, which will start slower at the beginning, and at the middle it will be quicker, and at the end it will get slower again, so that we get that smooth curve that we saw in the video previously. And let's get to this execute single frame step, and that's where we actually get I just got stuck in this watchdog problem. Here, if you look, as now, whatever you have read, we have just going through this coordinate S curve move, right? This all is going to be executed by CPU. So the CPU will be busy, like to call that function. Everything is zeros and ones. Like I cannot get to the compiler designs yet, but everything is zeros and ones to the CPU. So the instruction register will just get this function with these values embedded in other formats into the function, and it will apply that target base, target shoulder into this, and this target shoulder, target elbow, everything will be rephrased with this current base, and those values will be given to this execute single frame step. So at this instant, how much ever I have explained, everything is going to be executed by CPU without any rest or feeding its watchdog. Watchdog is nothing but, hey CPU, are you still alive? Not like more like is it alive? It's more like, have you got into any loop? Like, even we know that computers can get into an infinite loop, and that's why there is this watchdog in every microcontrollers. It asks the CPU, are you available after every 20 milliseconds, so that it knows that okay, the CPU is executing, knowing that the the watchdog is fed every 20 milliseconds, so that we get to know that the CPU is not getting into any infinite loops, so that it can just stop everything what it is doing. And that's where this everything will not work when we call this out. Execute single frame step is also calling this assembly function to execute by the CPU. So the CPU will not be free here either. So we need to feed that watchdog when we are waiting for this 1000 millisecond. So we cannot call this function, though this is just gonna wait the CPU cycles. It doesn't mean that it will keep the CPU free. So for that we call this v task delay with pdms to ticks. Ticks in the sense it is more like the cycles. Mostly AI models tell that it is 240 megahertz, but my microcontroller is actually 160 megahertz. And I got to know that when I just get to the monitor screen, and it shows like the CPU clock speed is 160 megahertz. And you just make sure that you go through that as well. And one final thing that I would say is that kindly, if you're going to go with this manually set it up environment to get your microcontrollers, get these informations compiled, make sure you use linux. Because if I tried using, I did use windows, but whenever I connect that with the ttl converter, mostly they fail. Out of 5 chances, 4 fails and only one gets executed. And linux at the other hand, it is always like it is very quick, which makes our work even faster. It's more like it doesn't mean like can I learn this? It's more like it's just some bunch of commands that you must run in your terminal windows, which will ultimately install those all in your terminal for you. And you can just get assistant from your AI models, and you can just learn them all. And in our next videos, we'll be going through the inverse kinematics, and then later on with AI models integrating into microcontrollers, sometimes maybe edge AI. We have a lot to learn. Watch you in the next one.